Good morning. Welcome to another session of EE403 Distributed Generation and Smart Grids. In this session, we will see solar power systems and small-scale hydroelectric power generation. Before we proceed, let us see a quote by Dr. APJ Abdul Kalam. All birds find shelter during rain, but eagle avoids rain by flying above the clouds. So we are in module 2. So today we will see solar photovoltaic or PV systems and small scale hydroelectric power generation. Wind energy conversion systems we will see in the next session. So starting with solar PV systems. So this is a picture showing a solar PV system installed in a typical home. You can see that the output of the solar panels, that is DC, from the panel, it goes to a on-off type of switch, and then it goes to a power conditioning unit, and from here it goes to battery banks, and also it goes to another AC on-off system, and there is an AC main panel, and there are typical AC load sockets, and from here it goes to the electric meter, and then it is connected to the grid. So this power conditioning unit is the heart of this. It contains conversion systems from DC to AC, because this side is AC and this side is DC. Also it also contains a charge controller. So the advantages of a PV system are they do not harm the nature, so it's a sustainable nature of solar energy. The environmental impact is minimum. The customer can install it in his or her premises, so over a period of time he gets electricity totally free. So the lifetime is almost like 3 decades, and it requires minimum maintenance, and the operation is silent, and maintenance is basically cleaning the solar panels regularly. The disadvantage is the high installation cost and the low energy efficiency. The photocurrent produced by a cell is directly related to its surface area, incident radiance, and ambient temperature. So these 3 factors basically are proportional to the photocurrent produced by a PV cell. Metal contacts on the top and bottom of PV cell draws off the current to the external loads. So this is a picture of a typical PV cell. You can see a P-type bottom and type silicon in the top, and the junction, as the sunlight reaches the junction, it emits electrons and holes, and this flow of electrons and holes through the external load constitutes a current. So solar energy reaches the PV cell in 2 components. One as direct radiation, it's almost 85%, and 15% by diffusion in the atmosphere. So the PV cell behaves as a photodiode. Light energy incident on the cell surface generates electron hole pairs as current carriers at the PN junction. Now the generated voltage is limited by the forward voltage drop across the PN junction. So typically you know that the forward voltage is something like 0.3 or 0.6. So normally we get only about half a volt from a typical solar cell. So if you consider a typical 12 volt panel, about 25 inches by 54 inches will contain approximately 36 cells wired in series to produce about 17 volts peak output. Cells are arranged in series parallel combination to produce modules of higher voltage and power rating. PV modules are equipped with maximum power point tracking systems that maximizes the power output from the modules by shifting the operating point depending on the solar irradiance. There are different types of PV cells. Main PV cell categories are crystalline silicon and thin film. And crystalline silicon can be further classified into monocrystalline and polycrystalline. And thin film can be classified further into amorphous silicon. Now, various types of PV cell. First one is the monocrystalline silicon. Second is the multicrystalline silicon. Third is the thin film silicon. And the fourth is the hybrid one. So first, monocrystalline silicon. It consists of cells socket from a single cylindrical crystal of silicon. So it is shown in figure. Multicrystalline silicon made from cells cut from an ignot of melted and recrystallized silicon. Silicon is deposited in a continuous process onto a base material, giving a fine-grained sparkling appearance. The cell is encapsulated in a transparent insulating polymer with a tempered glass cover and usually bound into a strong aluminum frame. The solar cell manufacturing process is shown here as figures. Thirdly, the thin film silicon. Amorphous silicon cells are made from silicon atoms in a thin homogeneous layer rather than a crystalline structure. So other light sensitive materials like cadmium telluride and copper indium diselenide are also used for thin film PV cells. And hybrid combines the good qualities of both types of cells. So combine both monocrystalline and thin film silicons to produce cells with the best features of both technologies. So new hybrid solar cells generate 5 times more energy by harnessing sunlight and heat at the same time. This is a comparison of various types of PV cells and its conversion efficiency. You can see that the crystalline structure has efficiencies ranging between 10 to 17%, whereas gallium arsenide has efficiencies up to 30%. The conversion efficiency formula is electric energy output divided by energy of insolation on cell into 100%. This is a comparison of various technologies. So you can see the cell efficiency is highest for the hybrid, around 18 to 19%, then followed by monocrystalline. The module efficiency is also the highest for hybrid, which goes up to 17%. Area needed per kilowatt peak, this also you can see it is minimum for hybrid, 6 to 6.5 only meter square. Annual energy generated per kilowatt peak is again maximum for hybrid 865. Annual energy generated per meter square, this also is maximum for hybrid 139 to 150 kilowatt hour per meter square. And again annual carbon dioxide savings per kilowatt peak is highest for hybrid 499 kg plus kilowatt hour watt peak, and annual carbon dioxide savings per meter square is again highest for hybrid. So in general, hybrid technology is quite promising. Now we move to small scale hydroelectric power generation. Small hydro can be classified as shown in picture. 5 kilowatt and below we call it pico, 100 kilowatt and below we call it micro, 2000 kilowatt and below we call it mini, and 25,000 kilowatt and below we call it small. So even if you have a small waterfall, you can go for a pico or micro type of hydro generation. A small scale hydroelectric power generation generates electrical power between 100 kilowatt to 1 megawatt. Feeding this generated power directly into the utility grid or as part of a large standalone scheme powering more than one household. And this type of power generation can be used for generating on-site power in microgrids. Capacity factor is defined as the ratio of available annual energy to its rated annual capacity. This is the equation for the power output of a small scale hydroelectric power generation. P is the power output in watts, Q is the water flow rate in meter cube per second, H is the effective head, eta is the overall efficiency, rho is the water density, and G is the acceleration due to gravity. So here you can see the water density, acceleration due to gravity. These factors we cannot change. So the power output basically depends on Q, H and eta. Okay. So these are some of the references. Please go through them at home. And with that, we end this session. This is Dr. Unnikrishnan PC signing off. We will see again with another topic in the next session. Thank you very much.